Hi everyone. Our topic for today is mass wasting. Um, the video is divided into part 1 and part 2, and we're having the part 1 today. I'm Dr. Sandra G. Catane. I'm the lecturer and your teacher for today. On February 17, 2006, a massive rock slide avalanche occurred in St. Bernard, southern Leyte. It buried the entire village of Ginsaogon with 14 to 18 cubic kilometers of rock debris, resulting to death toll of 1,119. The landslide is considered as one of the largest single landslide event in the Philippines. This lecture covers one of the most hazardous events in the Philippines, termed mass wasting and landslide hazards. Let's examine the definition of landslides. Landslide is a general term for downslope mass movement. In the common usage, it implies rapid motion that potentially kill people along their path. Mass wasting is a more general term as it includes slow landslides such as creep and slow flows. Mass wasting, slope failure, and landslides have been used in the literature to describe similar phenomenon. The main driving mechanism of landslides is gravity. Now we go to the classification of landslides. Landslides are classified based on type of materials involved, the speed or velocity, and the type or mechanism of downslope movement. Landslides are classified into fall, topple, flow, slide, and subsidence. In the diagram or in the figure, you can see the illustration of the different types of landslides based on mechanism. This is flow, slide, fall, toppling, and subsidence. What are the types of material involved? Could be rock, which is a firm mass that was intact in its natural place before the initiation of movement. Soil is an aggregate of minerals and rocks that either was transported or was formed by weathering of rocks in place. You can also subdivide soil into two. Earth, if 2 millimeter particles is greater than 80%. Debris, if 2 millimeter particles is less than 20%. How fast are landslides? Can be very slow. Example is a creep. Could be moderate velocities, slumps and earth flows. And rapid to very rapid types of landslides such as rock falls and avalanches. Classification of landslides. This table is authored by Barnes. He introduced this classification in 1978. From then on, many authors use this classification to describe or classify landslides. Barnes based his classification on two main parameters, type of movement and the type of material involved. He showed several mechanisms here: falls, topples, slides, spreads, flows, and complex types. Falls are detachment of material from a steep slope along a surface with little or no shear displacement. The material descends mainly by falling, bouncing, or rolling. Topple, there is a forward rotation out of the slope of materials about the point or axis below the center of gravity of the displaced mass. Slides, movement occurs dominantly on surfaces of rupture or on relatively thin zones of intense shear strain. There are two types of landslides depending on the motion. We have the rotational and translational. Spreads refers to the extension of cohesive soil or rock mass combined with the general subsidence of the fractured mass of cohesive material into softer underlying material. Flows are spatially continuous movements. What I'm saying is that flows normally entrain particles, individual particles that move with respect to each other. And normally, the surfaces of shear are short-lived, closely spaced, and not usually preserved. Distribution of velocities in the displacing mass is like a viscous fluid. Complex type of landslide involves several mechanisms. Can be a combination of the different mechanisms enumerated here, like a fall transitioning to slides, and then they become flows. Carson and Kirkby in 1972 introduced another way of classifying landslides. They classified landslides and slope failures based on speed from creep to slides. The destructive potential of a landslide increases with speed. The type of movement is also dependent on water content. With increasing water content, the movement changes from sliding to flowing. Water content changes the mechanism of movement from very rapid landslides to somewhat slower flows and slurries such as earth flows and mud flows. Now we go to the description of each type of mechanism. First is fall. As you can see, the mechanism of fall is illustrated in this caricature. Rock falls are common in rugged terrains where slopes are oversteepened by processes such as wave erosion and undercutting by streams and rivers or road cuts. Examples are the rock falls along the Colorado River, Sicamane Valley, British Columbia. These are the rock falls. This is a rock quarry in Guangxi, China. You have rock falls here. And a lot of rock falls along the Halsema Highway, Philippines, that's located in Mountain Province and Benguet. Topples. Topples can be seen in many examples. Topple failure involves the forward rotation and movement of rocks. Could be ice or regolith out of the slope at a point or at an axis. It is common where there is a pronounced vertical or steeply dipping discontinuity in a rock formation. Examples presented here is along Chaco Canyon. This is a block which is about to rotate or topple. We have here also an active topple in Charmant, United Kingdom. This is a perfect candidate for toppling failure. Slide. We can see here the two types of landslide of slides. This is the rotational type, and this one is the translational type. In rotational type, you have, of course, a rotation that's involved in the downslope movement of mass, of this mass. In translational motion, normally the movement is along a plane, a shear plane. Normally, this block is intact as it moves down the slope. Slide occurs when there is a distinct zone of weakness that separates the slide material from the more stable underlying material. In rotational landslides, this slide in which the surface of rupture is curved concavely upward, this slide movement is roughly rotational about this axis, and it's parallel to the ground. Translational landslide, where the landslide mass moves along a roughly planar surface with little rotation or back tilting. Block slide is a translational slide in which the mass consists of a single unit like this, or a few closely related units that move downslope a relatively coherent mass. Examples here are the Liad River. This is a rotational type. Valtellina in Italy, it's a translational type. And those found in Halsema Highway are also translational type. Spread or lateral spread or flow refers to landslides that commonly form on gentle slopes or flat slopes that have rapid fluid-like flow movement similar to water. It is common in loose sediments consisting of sand, clay, and silt that are found along fluvial and coastal environments. In the 1964 Alaskan earthquake, with the moment magnitude of 9.2, the earthquake caused extensive lateral spreads and liquefaction features that occurred during the earthquake. It was a landmark event in geotechnical engineering at the time when the effects of spreads and liquefaction were not fully understood. These are the damages produced by liquefaction and lateral spreading in Alaska in 1964. Just a few months later, in Japan, Niigata, Japan, an earthquake triggered a spectacular liquefaction and lateral spreads. Liquefaction in sand layers and in sand or silt seams in the clayey soil beneath the anchorage caused many of the destructive landslides that occurred during that earthquake. Liquefied seams and lenses disturbed the sensitive clays caused their strength to drop below the levels needed for stability. On this side is an example of lateral spreads. Look at this block here detached from the side of the canyon. In the Liard River in British Columbia, lateral spreads are quite common. Flows can be wet or dry. This diagram shows landslide type, the flow type, landslide. And in the other examples, for example, in El Salvador, an earthquake with magnitude of 7.7 on January 13, 2001, triggered an earth flow covering about 400 houses with mud and resulting to 844 deaths. Fed by loose sediments from the Mount Pinatubo eruption, rainfalls generated lahars which prevailed for about 10 years but slowly diminished when watersheds on the slopes of the volcano started to stabilize when vegetation started to recover. This is another example of flow. It's the PL landslide in Washington State. look at the shape of the deposit, it shows a flow-like morphology. Another example of a flow is the Ginsaogan landslide in southern Leyte. This landslide is termed rock slide debris avalanche. If you look at the photo, it has this characteristic hammocky topography. This is another example of a landslide, which is of the flow type. This is the landslide that was produced by the Cotabato earthquake in 2009. The next type of landslide is creep. Creep is the slowest kind of landslide. A creep has a definite steady movement of soil under the direction of low shear stresses. Downward movement in a creep is slow and steady. It can occur in gentle slopes. When a clay in the soil on a hillside absorbs water, it will expand, causing the soil to swell. As the clay dries and contracts, the particles settle slightly in the downhill direction. Slow creep movements can precede the initial failure of a slope, meaning creeps can be a precursor to a larger landslide. If you look at this diagram, you can see that the structures on top of the soil that's moving or creeping are affected by the movement. This is a fence affected by creeping. This is an actual illustration of this caricature showing creep motion on the surface of the bedrock. Along Halsema Highway, it's not very clear from this photograph, but you can see the bending of the soft rocks, indicating that creeping is occurring on this slope. Next is complex types of landslides. Complex types are in combination of the different mechanisms. They can transition from one type to another. For example, from backsliding to falling to avalanching. Example is the Frank slide, the Trisel slide in Utah, Huascaran avalanche in Peru, and Colon landslide in Mankayan. The Ginsaogan rock slide debris avalanche is another example of a complex landslide. Complex landslides are commonly those of large volume. The largest and most far-reaching landslides on Earth are the submarine landslides at the borders of the chain of volcanoes in Hawaii. The map here shows a broad belt of chaotic terrain, or we call them as landslide deposits, that extends hundreds of kilometers across the seafloor adjacent to the Hawaiian Islands. They are interpreted as massive landslide deposits that originated from steep unstable submarine flanks of the volcano. Mauna Kea in the Big Island rises at 4,205 meters above sea level but extends about 6,000 meters below sea level to meet the deep ocean floor. Its total height is therefore about 10,211 meters, considerably higher than that of the height of the tallest mountain on land, which is the Mount Everest, which has a height of 8,848 above sea level. This makes the Hawaiian Shield volcanoes the largest and highest mountains on Earth, which make them prone to slope failure. Next topic is angle of repose. We define angle of repose as the maximum slope angle at which the material is stable. Landslide involves driving forces and resisting forces. Driving forces can be the mass of the material, gravity, or pore pressure. Driving forces are those that tends to induce downslope movement, while resisting forces are those that tend to keep the material intact on the slope, which include inertia, friction, and diffusion. Water has an important role in slope stability. This figure demonstrates the angle of repose of unconsolidated materials. In A, wet sand can be piled up steeply, but in B, dry sand will always come to rest in a cone-shaped mound with slopes of about 32 to 34 degrees. In A, the angle is roughly 80 degrees. This is moist sand, this is dry sand. In C, coarse material such as gravel will have a steeper angle of repose than dry sand. In these two cases, both are dry. Moisture content and the angularity of particles can also affect a material's angle of repose. The effect of water is illustrated in this diagram. Water has an important role in slope stability. Pore space is mostly occupied by air, but with small amount of water, it produces a capillary force which holds the particles together, resulting in more cohesion and allowing a high angle of repose. This is true in the case of the previous diagram showing the steep angle of the moist sand. In extreme case, a large amount of water occupying all pore spaces exerts pressure on the particles. We call it as pore pressure, which tends to keep the particles apart and allowing them to flow more readily. The cohesion is reduced in this case. Further, the effect of water, as you can see, in the dry sand, a slope can be attained at 32 to 34 degrees in dry sand. In moist sand, you can have steep angle or angle of repose because of the capillary force acting within the pore spaces. And however, if the pore spaces is saturated with water, the tendency is that the angle of repose is lowest. Another effect of adding water to a slope is to increase the mass of the slope, hence the gravitational pull on the slope, which favors mass movement. Effect of slope angle. Forces acting on a piece of rock on an inclined surface. The weight of the rock is divided into two components, dF, or driving force, and Fp, force perpendicular to the plane. The steeper the slope, the greater the component of the weight that acts parallel to the slope, or we call it as the driving force. The boulder is restrained from the resisting forces, that is friction. If the driving force is greater than the resisting force, the rock moves down. When the driving force and resisting force are equal, the rock is considered to be in state of equilibrium and it will remain stationary. In this diagram, you can see that a lower angle of the slope makes the boulder stable compared with in this illustration where you have a steeper angle. How do engineers evaluate the stability of slopes? Slope stability is determined from the universal term called factor of safety, or FS. It is the ratio of the resisting force and driving force. RF is measured in the laboratory and DF is calculated using trigonometry. The factor of safety, if the factor of safety is equal to 1, then RF, or resisting force, is greater than the driving force, then the slope is stable. This relationship is the simplest way of showing how the factor of safety is affected. There are more complex relationship or equations that can demonstrate the factor of safety of a slope. For most modern building codes, they require a factor of safety of 1.5. For major infrastructures like dams, they require a factor of safety of 3.5 or higher. These are landslides triggered by water input. Water infiltrating on the stable slope increases pore pressure. The effect is it loosens the particles and add more weight to the slope, favoring failure. The mudslide after the Hurricane Mitch in 1998, and this one is a slope failure in Micabre, California in 2000. Rainfall-induced landslides. Heavy rains brought by low pressure on December 17 to 20 in 2003 triggered numerous landslides in Panaon Island, southern Leyte, resulting to 154 deaths. In this site alone, in Barangay Liloan, there were almost 150 people buried by a single landslide. On February 17, 2006, a massive rock slide avalanche occurred in St. Bernard, southern Leyte. It buried the entire town or village of Ginsaugon with 14 to 18 cubic kilometers of rock debris, resulting to a death toll of 1,119. The landslide is considered as one of the largest single landslide event in the Philippines in terms of volume and number of casualties. It is not clear as to the trigger, but moderate rainfall, small magnitude earthquakes preceding the landslide are possible. Alternatively, progressive tectonic weakening of the slopes is also a feasible explanation of the trigger. The foot of the bridge at the photo is part of the latest segment of the Philippine Fault Zone. This area is experiencing small magnitude earthquakes from time to time. So the earth movements can have an effect in loosening up the materials on the slope, leading to the disastrous landslide that occurred in 2006. The Cherry Hills landslide. In August 3, 1999, a landslide occurred in Cherry Hills subdivision in Antipolo, Rizal province, resulting to the death of 60 people. The landslide is attributed to the 33 consecutive days of rainfall caused by a distal typhoon Ising, international name Olga, as the site was being developed for the expansion of the Cherry Hills subdivision. Earthworks here and here have destabilized the slopes along with contributory factors such as the low rock mass strength of the materials on the slopes. That ends the first part of the lecture on mass wasting. Thank you for watching. And for the last slide, it's just a warning.